Hello everybody, my name is Xiaoyu and I am sharing my presentation on my research paper, a comprehensive analysis and development of electric drive wheel with idler gear. My contents include the following 6 parts: introduction of the research background, research objective, longitudinal characteristic analysis, vertical characteristic analysis, prototype and test, and finally, conclusions. The electric drive wheel is a promising propulsion technology for electric vehicle, which can realize independent control and power output of every single wheel. The electric drive wheel has a short transmission chain and a fast response speed, which significantly improves the vehicle's maneuverability. According to the power transmission paths, the typical EDW can be divided into 2 schemes. One is direct drive EDW, and the other is speed-reduced EDW. The direct drive EDW has difficulties to balance the efficiency and performance of low speed and high speed, especially when the vehicle is accelerating or climbing at a low speed. On the other hand, the speed-reduced EDW can adopt a PMSW, permanent magnet synchronized motor with high-speed capability, which can fully use the high-efficiency range of the electric motor and cover the various demands of the vehicle. From the perspective of automotive engineering, the EDW is an integrated execution unit that combines the function of powertrain and suspension. As a result, the research on EDW involves the intersection of multiple disciplines. In this paper, we developed a novel speed-reduced EDW with idler gear, which is based on the traditional planetary gear configuration and evolved further to achieve a higher transmission ratio and a higher torque density. When we set the EDW as a research objective, we are seeking for indicators of output performance. For a given EDW design, the output performance of EDW has a direct impact on the dynamic performance of the vehicle. For example, the longitudinal dynamic characteristics of EDW are carried out under geometric constraints, which involves gear meshing performance and load sharing performance. In addition, the vertical dynamic characteristics of EDW are related to vehicle comfort ride. Usually, differential equations are established to study tire grounding characteristics and wheel dynamic loads. For these complex working conditions, it is necessary to model and analyze them one by one and study the principle of how each parameter works in the system. A virtual prototype was built for the CAE simulation, and a physical prototype was made for the bench test, both of which were analyzed to validate the theoretical principles. The basic structure of an EDW with idler gear configuration includes a wheel assembly, a drive motor, a transmission system, and a brake system, all of which are installed on an integrated housing. The drive motor biased at the wheel center position and the 2 idler gears are arranged symmetrically. When the vehicle is driving, the motor gear transmits the motor torque, then meshes with the 2 idler gears simultaneously, and ultimately drives the wheels. The Figure 3, Evolution of Transmission System Configuration. The red line represents the center line and the angular displacement generated by the external meshing between the motor gear and the idler gear. The blue line represents the center line and the angular displacement generated by the internal meshing between the idler gear and the ring gear. The planetary gears were symmetrically arranged as the x-axis, and the central lines of all gears were connected in a straight line, as shown in Figure 3a. When the center of the planetary gear deviated from the x-axis and was symmetrically arranged in the 3rd and 4th quadrants, the connecting lines of each gear center formed a symmetrical intersection angle, as shown in Figure 3b. From figure 3b, the sun gear was offset along the y-axis by a certain distance, resulting in figure 3c. At this stage, the sun gear was no longer in a symmetrical center position, so the sun gear was converted into a motor gear, and the planetary gear was converted into an idler gear. At this stage, the connecting lines of each gear center formed a converge quadratically. Figure 3D is based on the figure 3C, in which the motor gear and the idler gear were rotated by a certain angle together. Figure 3D allows for the free definition of the motor gear position. Their corresponding relationships have also become parameter variables that can be optimized. The EDW adopts an idler gear configuration with the motor gear connected to the motor rotor shaft. The motor gear transmits power by meshing with two idler gears symmetrically arranged. The two idler gears simultaneously mesh with the ring gear. The ring gear is connected to the wheel rim, ultimately driving the vehicle. In this transmission system, a coordinated system is established with the center of the ring gear as the origin. All components only rotate on their one center line without revolving. In the design phase, we assume that the motor has an ideal uniform air gap state without machining and assembly errors. The motor rotor can be simplified as the torsion spring with weak damping characteristics. On the premise of satisfying the geometric constraints of the idler gear, we defined three sets of gear parameters for simulation analysis, namely Plan 1, Plan 2, and Plan 3. The gear parameters are shown in Table 2. The simulation results are meshing stiffness and meshing force, respectively. The external and internal meshing force load sharing characteristic simulations are shown in the Figure 9 and Figure 10. According to the simulation results, we can see that under the premise of idler gear meshing, the smaller the gear modular was, the better its load sharing characteristics were, and the smoother the power transmission was. However, an extremely small modulus will reduce the gear strength and is constrained by gear manufacturing process conditions. Therefore, when engineering design and development, it is necessary to find a balance. The EDW model is shown in Figure 11. The vehicle vibration mode can be simplified as the 1-4 vehicle body vibration model of true degree of freedom in the vertical direction. As the position of the motor is not concentric with the wheel, the position of the motor center of mass has a certain impact on the vertical performance. Relevant variables are introduced for modeling and analysis. Among them, M2 is the body mass and only undergoes vertical vibration. M1 is the mass of the wheel assembly, and M0 is the mass of the motor assembly. The length of the swing arm from the wheel center to the suspension hinge point is A, and the length of the swing arm from the motor center of mass to the suspension hinge point is B. Alpha is the rotation angle of the swing arm. Beta is the rotation angle of the motor mass center. And the J0 is the moment of inertia of the motor passing through its one center of mass and parallel to the swing center axis of the swing arm. Figure 13 shows the acceleration of the vehicle body. We can see that the motor swing arm B exhibited a monotonic positive correction with the acceleration of the vehicle body. At the same time, the motor angle beta had a non-monotonic effect, and the beta achieved a minimum value at the position approaching the alpha angle. Figure 14 shows the dynamic load on the wheels. We can see that both the motor swing arm B and the motor angle beta exhibit a monotonic positive correlation with the variation of vehicle acceleration. In engineering design for the smallest possible wheel dynamic load, motor swing arm B should be shortened and the motor angle beta should be increased as much as possible under the premise of actual conditions. The comparison between the preferred solution and the initial state of this case is shown in Table 4. We can see that the initial acceleration of the vehicle body was relatively high, while the optimized state considered both the vehicle body acceleration and the wheel dynamic load, resulting in a more balanced overall performance that could adapt to the needs of more working conditions. Because the two objective functions could not simultaneously obtain the minimal value, the genetic algorithm was used for multi-objective optimization. After repeated iteration, a set of Pareto frontiers was obtained. In this case, we took an optimized state to balance the indicators of vehicle body acceleration and wheel dynamic load, as shown in Figure 15. The rotational velocity of each gear is shown in Figure 32, where the negative value stands for the opposite rotational direction. We can see that all the transmission components worked as expected throughout the whole working range. The motor gear rotational velocity started from 3 warm-up cycles under 3000 RPM. Then it rose with intense fluctuations between 500 RPM and 6000 RPM. Then the motor gear rotational velocity rose to the peak of 7500 RPM. Finally, the motor gear remained at 7500 RPM for 1 minute and then gradually stopped. We can see that through the whole working range, the ring gear curve followed perfectly with the time domain. Finally, the conclusions. This paper provides a comprehensive analysis of the performance of the EDW with idler gear. Based on this, we developed the engineering prototype for test. Conclusions were as follows. The evolution of the idler configuration requires geometric constraints that meet certain conditions. Under this premise, the smaller the modulo of the gear is, the better its load sharing characteristics are, and the smoother the power transmission is. However, an extremely small modulus will reduce the strength of the gear and is constrained by the manufacturing process conditions of the gear. Therefore, when designing and developing, it is necessary to find a balance. The vertical characteristics of the idler system are influenced by the position of the motor. However, the position of the motor is constrained by the installation space and the geometric relationship of gear meshing, making it difficult to follow the optimal principle of vertical characteristics in practical development. For a given design state of motor and a transmission mechanism, targeted optimization can also be achieved by adjusting the suspension K and C values. The prototype was equipped with a test bench covering a wide range of rotational speeds and diverse operating conditions. The performance of cycle conditions met the design expectations. In order to investigate the dynamic performance of the system, targeted torque step tests were conducted, and the output speed followed agilely with small overshoot wave momentary, reflecting good smoothness in longitudinal dynamics. Last but not least, the prototype was measured to be 38.2 kilometers, which showed good lightweight performance. My presentation is finished now. Thank you for listening.